This screencast will go through an example focused on determining the hydrostatic forces on an inclined plane surface. Specifically, let's look at this case where we have a rotating gate that is braced to prevent water from spilling out of a reservoir. The brace is between the gate and a movable stop such that the angle, which we'll designate as theta, can be varied. Now let's find the force the brace exerts on the gate as a function of theta, the gate length, which we'll designate as LG, and the brace length, which we'll designate as LB. With any problem, the first place to start is by drawing a picture. And you see we have a pretty good picture of the system already here. So since we want to determine the forces, we should start with a free body diagram on the gate. So let's start by drawing our gate, and we'll draw our brace acting against that gate, and we'll label some kind of origin. So we'll start down here at the pivot, and we'll say that in the up direction we have our y, and in the horizontal we have our x. So at this point we're going to call this the force from the brace. We have a weight force acting down through the center of the gate, and we have the force acting from the water on the gate, which we're going to designate as Fr, for the resultant force from the water acting on the gate. So to keep going from here, we need forces in the horizontal and vertical axes. So we need to label another angle in this picture, which we'll call phi. This allows us to write the force from the brace in the vertical axis as Fb sine phi, and in the horizontal axis as Fb cosine phi. So we'll need some more lengths to accurately represent this system. The horizontal distance, origin to where weight acts through the gate, is going to be L sub g divided by 2 cosine theta. The total distance from the origin to where the brace acts on the gate, and this is just going to be Lg cosine theta. The resultant force from the water acting on the gate acts through the center of pressure, which for a gate like this would be 2/3 from the top or 1/3 from the origin. So we would designate this distance as Lg over 3. The two vertical distances that we care about are from the origin to the center of the gate where the weight acts, and this is going to be Lg over 2 sine theta, and from the origin to where the brace acts, which is the top of the gate, and this distance is going to be Lg sine theta. At this point we could write our force balance on the gate, and we know that the sum of all forces must be 0. So this means the force acting in the clockwise direction must be balanced with that acting in the counterclockwise direction. So when we do our force balance, the force of the water acting on the gate is the resultant force, Fr, times the distance of which it's acting. So we write Lg over 3. This is going to be plus the weight force from the gate, and this is times the distance from the origin that force acts, which is Lg over 2 cosine theta. This is going to equal the counterclockwise direction, so the force from the brace in the horizontal direction, so cosine phi, times its distance from the origin, Lg sine theta, plus the brace force acting in the vertical direction, Fb sine phi, times the distance from the origin, which will be Lg cosine theta. We know that the resultant force, Fr, can be rewritten as the specific weight times the height to the center times the area at which it's acting. In this vertical distance, hc, we know as the height to the center, so we could rewrite this as a specific weight of water times Lg over 2 sine theta times the area Lg times some width that's acting into the paper for the gate as W. At this point we'll plug in the resultant force into this first equation and rewrite it so it looks like the following. At this point we could divide the whole equation by the length of the gate and solve for Fb. We need a relationship between theta and phi. And if we draw our diagram again, we know that this angle is theta, this angle is phi. We could draw two triangles where we know this distance to be the length of the gate, this distance to be the length of the brace, and we could say that the length of the gate, sine theta, is equal to the length of the brace, sine phi, since it each equals this common length inside the triangle. Therefore, we could say that theta is equal to the inverse sine of the length of the brace over the length of the gate times sine phi. And as much as plugging this back into this equation would be fun, I would suggest to use some kind of solver for using both equations so that you could plug in values for the weight of the gate, the specific weight of the water, the length of the gate, as well as the length of the brace, and then given a certain value of theta, you could therefore solve the force of the brace acting on the gate.